Okay, today we're going to be looking at tutorial 1a. The first problem amounts to solving a quadratic equation and manipulating quadratic functions. Problem revolves around using basic notations of probability and statistics in a quadratic equation problem that has a parameter in it that makes random values. 1. Non-linear supply and demand. Consider a market with a single good or service traded against a price P. Suppose the demand function of this good or service is given by demand, which is a function of P, is equal to 15 minus 5 over 3P plus 1 over 20P squared, and the supply function is supply, which is a function of price, is equal to 3P minus 1 over 8P squared. Now, an economist argues that if we want to use this model, then we should only use it on a range of prices where P is in a set 0 to P max, on which either demand function is a positive but declining function of price and the supply function is a positive and increasing function of price. Give one argument against or in favor of its view. So first what I'm going to do is try find P max, the maximum that price can be. To do that, I'm going to differentiate the demand function so that we get minus 5 over 3 plus 1 over 10p, and I'm going to equate this to 0 to find the maximum point. So we get minus 5 over 3 plus 1 over 10p, so 1 over 10p is equal to 5 over 3, so p ends up being 50 over 3, which is approximately 16.7. If I do the same with our supply function and differentiate it, we will get 3 minus 1 over 4p. If I equate this to 0, we get 0 is equal to 3 minus 4p, so 1 over 4p is equal to 3, so p is equal to 12. So now I'm just going to draw a rough sketch of this diagram. I'm going to put price on the x-axis, and I shall put quantity on this axis. When I do this, the demand is a downward sloping curve, so it looks something like this, where this point is equal to 16.7, and then supply is upward sloping, where this point is equal to, well, price is equal to 12 at that point. If I were to extend this line across, we would get something like that. And if I extended the demand function, we would get something like that. As you can see, when P is greater than 12, the supply curve becomes a decreasing function, which no longer agrees with the economist's model. That means the maximum price is going to be when P is equal to 12. So P max is equal to 12. If we now give it a reason for why the supply curve is upward sloping and why the demand curve is downward sloping, if we begin with the supply curve should be upward sloping due to firms having a profit incentive. Demand curve should be downward sloping due to the law of diminishing marginal utility. Consumers will only buy more when the price falls, hence why demand curve has that downward slope. Okay, moving on. If we look at the sketch the two functions of the interval 0 to 12, I'm first going to change the y-axis so it makes a bit more sense. We're going to go 0, 5, 10, 15, 20. If we first draw the supply curve, when we put 0, we will get 0. When we put 5, we get somewhere around 11.87. So that would be somewhere around here. When we put 10, we get 17.5, which would be somewhere around here. And when we put 12 in, we get 18, which would be somewhere around here. So we get this as our supply curve. Doing the same with demand, when we sub in 0, we get 15. When we sub in 5, we get 7.91, which will be somewhere around here. When we sub in 10, we get 3.3, which will be somewhere around here. And when we sub in 12, we get 2.2. So demand looks something like this. And there's our sketch done. Part C. Give the expected value of P and solve for the expected value of P is equal to 0 for P asterisk, where the expected value of P is the excess demand function. E, which is a function of P, is equal to quantity demanded minus quantity supplied, as that is what excess demand is. If I sub in the quantity demanded function and quantity supplied function, we get 15 minus 5 over 3p plus 1 over 20p squared minus 3p plus 1 over 8p squared. If I now equate this to 0, as that's what the question is asking for, we get 0 is equal to 15 minus 14 over 3p plus 7 over 40p squared. If I now solve this using quadratic formula, which is minus b plus or minus square root b squared minus 4ac all over 2a, where a is equal to 7 over 40, b is equal to 14 over 3, and c is equal to 15, we get p is equal to 22.9, or p is equal to 3.738. This one is invalid as it's outside our values of p, so we get 3.738, and our function e, which is a function of p, is equal to 15 minus 14 over 3p plus 7 over 40p squared. Moving on. Question 2. Consider the well-known quadratic equation ax squared plus bx plus c is equal to 0, and assume that the real numbers a and b are fixed and known, but c is a random variable, i.e. it can take n values of ci from the set Vn, each with probability pi. Why should we expect that sigma pj is equal to 1? So sigma nj is equal to 1, pj is equal to 1. So what this is saying is the sum of probabilities is equal to 1. We should expect this as the sum of all probabilities in a set should equate to 1. Pretty straightforward. If fc is a function of c, explain why the expected value of the function of c is given by e, f is equal to sigma, the probabilities, times by this function. Okay, if I rewrite this, sigma n j is equal to 1, the probabilities times this function, what this is saying is this is the expected value of the function of c. And to work out expected value, we have to do the probability times by the possible outcome of, and then what we do is we sum these together. So all the possible outcomes, we sum them together when we've times them by their probability. As you can see, that's what we're doing here. We have got the probability of a certain value from this function, and then we're going to sum together everything. So when we complete this summation, we shall get the expected value of c. Cool, moving on to c. If the variance sigma squared is equal to the expected value of x squared minus the expected value of x all squared, demonstrate that we have a sigma squared plus a expected value of x all squared plus b expected value of x plus the expected value of c is equal to 0, and give an expression for each of the x in terms of sigma. So I'm going to first start off with the general form of a quadratic, which is ax squared plus bx plus c. So this is the general form of the quadratic, of a quadratic. I'm now going to take expectations on both sides. Expectations on both sides. So I get the expected value of this whole equation is equal to the expected value of 0. The expected value of a constant is just the constant itself. So expected value of a constant is the constant itself. And what we can do is we can split this up as expectations are linear. What I mean by that is we can now write ax squared plus bx plus e to the c is equal to 0. And now what we can do is take out all the fixed constants. So we get ax squared plus bex plus ec is equal to 0. What I'm now going to do is rearrange our variance equation to make ex squared the subject. When I do this, I will get sigma squared plus ex all squared is equal to ex squared. And if I now sub this in to here, we get a sigma squared plus a expected value of x all squared plus b expected value of x plus the expected value of c is equal to 0, which is what they wanted, so we've demonstrated that. And now we need to give an expression for e to the x in terms of sigma. So hopefully we can see that this is a disguised quadratic. If I let y is equal to ex, or the expected value of x, we get a y squared plus by plus ec plus a sigma squared is equal to 0. So all of this is our constant c, and then this is b, and this is a when we look at the general form of a quadratic. So if we use quadratic formula now, minus b plus or minus square root b squared minus 4ac all over 2a, we get minus b plus or minus square root b squared minus 4a, and c is e to the c plus a sigma squared all over 2a. So that would be our answer to that.